Imagine you're standing at a cosmic crossroads. You need to make a choice. A decision tree is like a map for those choices. It's a simple yet powerful tool. Computers use these trees to think, to make predictions, to sort through the vast universe of data. What kind of data? All sorts. From whether a distant celestial object is a star or a quasar to deciding if you should take an umbrella today. It's about making sense of information, one step at a time. This is a fundamental concept in the world of artificial intelligence. Now, this idea fits into a bigger picture. We call it machine learning. That's where we teach computers to learn from data without being explicitly programmed for every single task. Decision trees are one of the many instruments in the machine learning orchestra. They can perform two main types of cosmic concerts. One is called classification. That's like sorting your cosmic rock collection into meteorites or Earth rocks. The other is regression. That's like predicting how bright a supernova will be. Big, complex questions, yet the tree itself can be surprisingly straightforward. Think about your own day. You wake up, you look outside. Is it raining? That's a question, a decision point. If yes, you might grab an umbrella. If no, you leave it behind. Maybe you then ask, is it cold? If yes, you grab a jacket. This series of questions, these branches of choices, that's a decision tree in action. You're using one right now in your own magnificent brain. Computers are just learning to do something similar, but often with much, much more data than you'd care to ponder over breakfast. So, a decision tree guides a computer. It helps the machine navigate through possibilities. It asks a sequence of simple questions. Each answer leads down a specific path. Follow the path and you arrive at a conclusion, a prediction, an answer. It's a logical flow from a general starting point to a specific outcome. It's like charting a course through an asteroid field, one careful turn at a time. And when you think about it, that's pretty amazing, isn't it? A simple structure making complex decisions. Every grand journey needs a starting point. On the map of a decision tree, this is the root node. Picture it as the sun in our solar system, the origin of all paths. This node holds all your initial data. All the possibilities are bundled together here. It asks the very first, most important question, a question designed to split the universe of your data into more manageable chunks. From this single point, the entire structure of decisions begins to unfold, branching out into the unknown. It's the genesis of the decision-making process. From this route, like great rivers flowing from a mountain source, branches emerge. Each branch represents a possible answer to the question posed by the node it came from. If the question at the root node was, is the celestial body larger than Jupiter? One branch might be yes and another no. These branches are the pathways. They lead you from one question to the next. Each choice you make, each answer you provide, sends you down a different branch. You're navigating the structure, moving deeper into the decision space, exploring the potential outcomes based on the evidence. Now, if you follow a branch, you might not reach your final answer immediately. Instead, you could arrive at an internal node. Think of this as a waypoint on your cosmic journey. Another checkpoint. Another question. This internal node takes the subset of data that came down its branch and asks a new question. It splits the data even further. It's all about refining the search, getting more specific. Each internal node is like a miniature root node for the data that reaches it, continuing the process of division and inquiry. Eventually, every path must end. Every branch, if followed long enough, will lead you to a leaf node. This is the destination, the final frontier of your decision path. No more questions are asked here. A leaf node represents the outcome, the prediction, the classification. If you were identifying stars, a leaf node might confidently declare this is a red dwarf. Or if predicting weather, high chance of meteor showers tonight, it's the final classification or the predicted value, the culmination of all the preceding questions and answers. That's the beauty of it. So, how does this magnificent tree decide which question to ask first? At the root or at any internal node? It's not random. The tree is smart. It wants to ask the most powerful question, the question that will best help it sort the data. Imagine you have a vast collection of astronomical images. Some are galaxies, some are nebulae, some are just lens flare. The tree wants to find the question that separates these categories most cleanly. It needs an optimal strategy for understanding the cosmos of data. The tree meticulously examines all the possible questions it could ask. For every feature in your dataset, it considers a split. For instance, if you're classifying celestial objects, it might ponder, does it have spiral arms, or is its apparent magnitude less than 5? Or is its redshift greater than 0.1? It then calculates how effective each of these questions would be at creating purer, more homogeneous groups of data. This evaluation is crucial. It's the tree's way of learning to ask the right things at the right time, a core aspect of its intelligence. Scientists have cool names for the metrics used here. You might hear about Gini impurity or entropy. Don't let the names intimidate you. Think of them as ways to measure messiness or disorder in a set of data. If a group of celestial objects is half galaxies and half nebulae, it's quite impure or has high entropy, it's mixed up. If it's almost all galaxies, it's purer with low entropy. The goal of the tree is to ask questions that reduce this impurity as much as possible with each split. Therefore, the tree chooses the question that results in the largest information gain. Information gain is just a fancy way of saying the biggest reduction in messiness. It picks the feature and the split point that create the most ordered, most separated subgroups. Once it makes that split, it has new, smaller groups of data, and for each of these new groups, if it's not yet a pure leaf node, the process repeats. It finds the next best question, and so on, until all data points reach a final decisive leaf node. It's a recursive process of refinement. Just like stars in the cosmos, decision trees come in different varieties. One common type is the classification tree. Its job is to predict a category, a label. For instance, is this newly discovered exoplanet habitable, yes or no? Or what type of galaxy is this image showing, spiral, elliptical, or irregular? These trees sort your data into distinct, predefined bins. They answer what kind? Questions. They are fundamental for tasks where the outcome is a specific class or group. Then there are regression trees. These are a different beast. They don't predict a category. They predict a continuous value, a number. For example, how far away is this star in light years, or what is the estimated mass of this black hole? These trees are used when the answer you're looking for isn't a simple label, but a quantity on a scale. So instead of a leaf node saying type A star, it might say surface temperature 9,000 Kelvin. They help us estimate and quantify aspects of the universe. Decision trees possess some stellar advantages. They are incredibly easy to understand and interpret. You can literally draw them out and see the flow of logic like a cosmic roadmap. They also require less data pre-processing compared to some other algorithms. They can handle both numerical and categorical data, but like any powerful cosmic tool, they have potential pitfalls. They can become overly complex, fitting the noise in your training data too closely. This is called overfitting. It's like mistaking a satellite for a new constellation. They can also be a bit unstable. Small changes in data can sometimes lead to a completely different tree structure. Throughout the history of machine learning, some truly brilliant minds have gifted us foundational decision tree algorithms. You might hear of ID3 developed by Ross Quinlan, which was one of the early game changers. Later, he developed C4.5, an even more robust successor. And then there's CART. That stands for Classification and Regression Trees. As its name suggests, this versatile algorithm can build both types of trees we discussed. These algorithms are the computational engines that allow us to construct these intricate decision-making structures from raw data, guiding our exploration of complex data sets.